one and all with warm greetings. Not merely words, our heartfelt feeling filled with emotions add flavor to welcome you. Our excellence in every field, on every occasion, in every walk of our life is being exemplified for your good sense. I, Dr. T. Bharati, welcome you all on behalf of Department of Mathematics, Loyola College, Chennai. Dear audience, today is the day we begin to learn by not looking into the eyes of others, where you will discover yourself. What God has given, no one can give. What He has designed, let us kindle. Prayer works wonder. Prayer should spring from the heart, thinking of the supreme power beyond all human inadequacies is a kind of auto-suggestion. Over to Professor Emmanuel for his musical ecstasy. Professor Emmanuel, for letting the goodness sparks to a spiritual chain reaction with your angelic voices. Let's invite our greeters to spray the sweet aroma of happiness through the words of welcome. Now I invite Dr. S. Adisyanathan, Coordinator Shift to Department of Mathematics, to deliver the welcome address.
Hello everyone. On behalf of PG and Research Department of Mathematics, Loyola College, Chennai, I am happy to welcome you all. Loyola College, Chennai is an institution run by the missionaries of the Society of Jesus, whose service towards education and humanity all over the world is highly appreciated and honored. Let your light shine is the motto of Loyola College, a premier temple of learning in South India, giving value education to the students. Loyola College was established with 3 departments, including the Department of Mathematics in the year 1925. The department was recognized as a research department in 1984. The Resin Research Center in Mathematics was established in 1991 on the occasion of the birth centenary of Reverend Father Charles Resin S.J., who was one of the big influences in the development of modern mathematics in India. Also, our department has formed many mathematicians all over the world. We are happy to organize this workshop on mathematical analysis. Mathematical analysis, one of the main and major branch of mathematics, deals with limits and related theories such as differentiation, integration, measure, infinite series, and analytical functions. Mathematical analysis is being constructed out of various contributions by famous mathematicians such as Archimedes, Bhaskara, Madhava, Newton, Leibniz, Euler, Cauchy, and others. Respected Dr. Lawrence J. Manoharan, the chief guest of the inaugural function, Dr. M.A. Bhaskar, head of the Department of Mathematics, Loyola College, Chennai, respected resource persons of the workshop from various reputed institutions, and my colleagues, it is my privilege and honor to welcome you all to this workshop. Respected professors, research scholars, my dear students and friends from various research institutions, universities, and colleges of our country and abroad participating in this workshop, it is my immense pleasure and joy to welcome each one of you to this 6-day online workshop on Mathematical Analysis MATANA 2020. During these 6 days, our resource persons will discuss recent developments on various topics in analysis. I hope that you will make use of this opportunity and develop your skills in mathematical analysis. Once again, I welcome you all. Thank you.
Thank you, sir. Let us now invite Dr. M.A. Bhaskar, Head Department of Mathematics, Loyola College, to deliver a descriptive and interesting address about MATANA 2020. Welcome, sir.
A very good morning to one and all. I am extremely happy to meet you all through this online program. This kind of workshop will provide us not only the essential knowledge but also a great opportunity to share experiences of technical and academic experts. Looking back through the history of mathematics, a French man of 16th century had migraine, the headache. Whenever he was suffering from headache, he could think of new concepts. All of you know about his contribution, the Pascal triangle. At the age of 16, Pascal presented a paper on projective geometry. So, if you have headache, think mathematics. In the year 1665, a boy was affected in Cambridge, England by plague. Almost all went to isolate themselves in the countryside. Among those was a young scholar of Trinity College. He went to a farmhouse called Woolsthorpe. It was there he invented calculus and many more. You can guess now, he was Newton, the great scientist. So, this pandemic may create modern scientists. Prepare yourself to be challenged and inspired. On behalf of the Department of Mathematics, I thank the Jesuit management for their encouragement and support for making this program possible. Thank you.
Thank you, sir, for your wonderful address. I am profusely overjoyed to take the opportunity to introduce our chief guest of the day. Yes, to be inspired is great, but to be an inspiration is an honor. It is a great privilege to welcome Professor R. Lawrence Joseph Manoharan, retired Head, Department of Mathematics, St. Joseph College, Trichy. Welcome, sir.
Dear friends, good morning. I thank the management of Loyola College for this opportunity given to me to be a resource person to deliver the inaugural address for this program. I congratulate the Department of Mathematics, Shift 1 and Shift 2 of Loyola College for organizing this program. And I learned they are doing a series of programs like this. And these programs are offered by the Department of Mathematics. It's a welcome feature. which will definitely benefit the staff of the departments of mathematics and also the students who are associated with research in MPhil and PhD level. Analysis is a very difficult subject, and many students find it very difficult. That is because they are not preparing the subject in the proper way, in the way it should be prepared. Real analysis cannot be studied only with the application of the mind. Application of the heart and soul is necessary for learning the subject, along with the application of the mind. So if you really want to learn analysis, whether it is real analysis or complex analysis, you have to apply not only your mind, but very deeply you have to apply your heart and soul into the concepts, into the theorems, into the problems. Only then you will be able to understand the subject very well, understand the concepts very well, and do the problems very well. You have to feel when you are doing a theorem in real analysis, or when you are studying a concept in real analysis, you have to feel not only with your mind but with your heart to understand the concept very well. That is very important for particularly the subject real analysis. Now, by way of inaugural address, I am going to give you a definition in functions of several variables, and also do a small problem based on the concept and based on a little theorem associated with the concept. Real analysis is itself difficult, and imagine functions of several variables. Definitely it is difficult. But if you study it in the way I have suggested that you should study it, definitely it will be very easy for you. Feel the subject. So, I am going to define the differentiation of a function of several variables. Just the definition I am going to give you. I am going to do a very small problem. With that, I will stop my lecture. That will be my inaugural lecture, and that is the lecture which will inaugurate this program. I am taking a function f. A function of several variables. So, first I consider an open subset E of Rn. E is an open subset of Rn. Now, you must understand why we are taking an open subset E. These are the questions you have to ask as you start studying the definition of the differentiation of a function of several variables. Open subset. Only in an open subset, every point will be an interior point. Because we are going to define differentiation. Differentiation involves limit, and the limit involves a neighborhood in which the function should be defined. So when you want a function to be defined in a neighborhood of a point, the function, the domain or the set in which it is defined has to be an open set. Of course, the same definition can be extended for closed sets also. In a proper way, it can be extended. So to avoid complications, we take an open set. So when I told you, you have to feel the definition with your heart also. This is what I mean. When you come across the word E is an open subset of Rn, you should start questioning. Why is it open? What happens when it is closed? What are the problems we face when the set is closed? And what happens when the set is neither open nor closed? Now, all these types of questions you have to ask yourself to study the definition very well, to understand the definition very well, and to apply the definition very well. This is precisely what I mean by saying that you should feel real analysis to understand real analysis. So I am taking a subset E, an open subset of Rn, and f is a function defined from E to Rn. Note that the domain is n dimensional, the codomain is m dimensional. Now you take x in E. X is any point in E, therefore there is no problem. It will have a neighborhood. I can talk about the limit. We say that the function f is differentiable at E. The function f has a total differential at the point E, at the point x in E, and the point x in E. I repeat, we say that the function f is differentiable at x in E, or we say that f has a total differential at the point x in E if the following thing happens. If there exists a, capital A function, a linear function from Rn to Rm such that limit h tending to 0 modulus of f of x plus h minus f of x minus a of h by modulus of h equal to 0. So look at this definition. We say f is differentiable at x. If I can find a linear transformation, A is a linear transformation. If I can find a linear transformation A from Rn to Rm such that this limit is equal to 0. Obviously, the definition is very, very intriguing, very difficult to understand. That is how real analysis will be. We have to analyze each word, each symbol that occurs in the definition properly to understand the definition. So remember, you have a modulus in the numerator. That modulus stands for the length of the vector. Modulus stands for the length of the vector. And you see the vectors in the numerator, f of x plus h, f of x, a of h. All these vectors are in Rm, in the codomain, Rm. They are all in Rm. They are all in Rm. So, the numerator is a vector in Rm in the codomain. We have to take the modulus there, that means we have to take the length in the m-dimensional space. In the denominator we have mod h. Remember, h is in the domain. Domain is n-dimensional. You have to take the modulus there in the n-dimensional space. So the modulus in the numerator is different from the modulus in the denominator. And as h tends to 0, this limit must be equal to 0. So we say that the function f is differentiable at the point x if I am able to find a linear transformation A from Rn to Rm satisfying this limit. The definition looks very, very complicated and far-fetched. Now, how to find this A? How to find this linear transformation? It should be a linear transformation from Rn to Rm. How to find this A? So, when the point varies, the linear transformation will vary. For the point x, you will get 1A. So, this is my E. It's an open subset of the domain. I take x here. I am defining differentiation at the point x. So for this x I am getting A. When I take a different point y, I will get some other b. In case the function is differentiable at that point. So for differentiability at a point, you have to find out this capital A, which is a linear transformation from Rn to Rm, and which obeys this limit, which obeys that limit equation. So it looks very difficult to find that A. Even in the case of very simple functions f, finding A is very difficult. But in real analysis, you must understand, all definitions are difficult. Definitions will be very lengthy. You take the definition of a Riemann integrable function. How do we define Riemann integration? The definition is very long. Definition is very long. How do we define a function of a bounded variation? The definition is very long. Similarly, the definition of differentiability at a point x for a function of several variables, the definition is very long. But fortunately, mathematicians, they are very clever people. You have to remember, you have to believe the mathematicians. Even though the definition is very long, they will find out some theorems which are very easily applicable based on the definition. And that is how the problems will be tackled. Seldom do we use the definition to do problems. Very, very rare. In fact, using the definition and doing problems is almost ruled out because it is going to be so difficult. It's going to be so difficult. Even to give an example, it is going to be very difficult. So once the definition is there will be some theorems based on the definition. And using the theorems, it will be very easy to give examples, to do problems, to develop the concept, and to develop the theory itself. This is what happens in functions of several variables, as it usually happens in any other subject of mathematics. I repeat, very rarely do we use the definition to do a problem, to solve a problem which is pertaining to the definition. For example, when you want to prove that a function is Riemann integrable, we never use the definition. We use only the theorems and conclude whether the function is Riemann integrable or not. Similarly for functions of bounded variation. Similarly for functions of several variables for finding out differential coefficient at a point. So this is what you must understand. But the definition, you must spend a lot of time thinking, reading again and again, point by point, understand the definition very well. Only then the theorems will be understood by you. If you know the definition very well, you will understand all the theorems very well in real analysis. And you will start doing problems. So concentrate on the definitions. Now, I am going to do a very simple problem to illustrate differential coefficient at a point x for a given function So I am using the book Rudin, Baby Rudy, Relenus for this definition. So from Baby Rudin, I am going to get you a problem, and I am going to solve that problem using a theorem. Now, what is a theorem? The theorem is, see, once the definition is there, there are many small results. For example, when A exists, that is when the function is differentiable at a point x, then that means A exists. A exists. When the A exists, it is unique. That is the first result which we prove after the definition. Then, when a function is differentiable at a point x, it will be continuous at that point x. That is the second result we use. So, these are all results which are available based on the definitions. Now, and the first theorem you have after the definition is, when a function is differentiable at a point x, all its partial derivatives will exist at that point. I repeat, this is the first theorem. After the definition of differential coefficient, the first theorem in function of several variables is, when a function is differentiable at a point x, then all the partial derivatives of that function will exist at that point, and they are given by a Jacobian, Jacobian. The Jacobian will exist. J is equal to dou f1 by dou x1, dou f2 by dou x1, like this. Here dou f1 by dou x2, like this it goes on. When a function is differentiable at a point, the Jacobian will exist. That is, all the partial derivatives will exist at that point. This is a theorem which follows immediately from the definition. Now, using this theorem, I am going to do a very simple problem to conclude this inaugural address. So, let me take a problem from Rudin. F of x comma y x cubed by x square plus y square, x comma y not equal to 0, equal to 0 at x comma y equal to 0. So at the origin, it takes the value 0, and at all points other than the origin, it is given by this equation x cubed by x square plus y square. So the question is this function differentiable at the origin? Is this function differentiable at the origin? It's a function of two variables. Fortunately, the codomain is a real number, is the real line. So remember, this function f is from R2 to R. R2 to R. So that f a, which is f dash of x, if it exists, that is, if the function is differentiable at the point x, then A will exist, and that A is going to be a 1 by 2 matrix. 1 by 2 matrix. So this will be dou f1 by dou x, dou f by dou x, dou f by dou y. There is a 1 by 2 matrix. It is having one row and two columns. 1 by 2 matrix. In general, if the function is f is from Rn to Rm, this A, which is f dash of x, will be an m by n matrix. It will be an m by n matrix. So this is your A. For this problem, it is going to be a 1 by 2 matrix. So this is it. Now I have to find dou f by dou x at the origin. This is at the origin. Because I am checking differentiability at the origin. So everything will be restricted to the point 0, 0, origin. So let me calculate dou f by dou x at the origin. This will be limit extending to 0, f of x comma 0 minus f of 0, 0 by x. And that will be equal to f of x comma 0 is, I have to put a y0 here, so it will be x cubed by x square. I have to put y0 here. And f of 0, 0 is given to be 0, so minus 0 by x. And this is, x gets cancelled, the answer is 1. So the partial derivative at the origin with respect to the variable x is 1. Now let me calculate dou f by dou x. Dou f by dou y at the origin. This will be limit y tending to 0, f of 0 y minus f of 0, 0 by y. And this will be limit y tending to 0. The f of 0 y means I must put x equal to 0 in this. When I put x equal to 0, this becomes 0. Minus f of 0, 0 is 0 by y. So the answer is 0. So the partial derivative with respect to x is 1 at the origin. It is 0 at the origin with respect to y. So I have to now write this A. What is this A? This A is 1 comma 0. A is 1 comma 0. Remember, A is 1 comma 0 at the origin. If it exists, so all this calculation, I am assuming the derivative exists at the origin. I am going to get a contradiction now. When I get a contradiction, that contradiction will be because I assume the derivative exists. So the derivative will cease to exist by the theory of reductio ad absurdum. So this is A. A is 1 comma 0, assuming that the derivative exists. Now, you go to that limit h tending to 0, f of x plus h minus f of x minus ah modulus by modulus h. This limit must be 0. This limit must be 0 for this A. Remember, when the A exists, it is unique. So that's why I have found out that A, and for this A, I will prove that the limit does not exist. That means the function is not differentiable at the origin. So this will be limit h tending to 0 modulus. Remember, at the point 0 I am calculating, so x is equal to 0. X is origin. I am calculating the derivative at the origin if it exists. So I must put x equal to 0. So this is f of h minus f of 0 minus ah by mod h. So this is limit h tending to 0 modulus of f of h. Remember, h is a two-dimensional variable domain. It is the domain, h is the domain. H is in R2. So it has it's a two-dimensional variable. So it's going to be f of h1 comma h2. And f of 0 is given to be 0. A, I have calculated it to be 1, 0. And this h is h1, h2. By modulus of h1, h2. Remember, in linear algebra, whenever you come across a vector, it will be a column vector. Unless otherwise stated, it will be a column vector. So all the vectors involved are all column vectors. So it's a column vector h1, h2. So this is equal to limit h1 into 0. F of h1, h2 I must substitute here. h1 cube by h1 square plus h2 square minus, when you multiply this matrix multiplication, this is 1 0 into h1 h2, this is 1 into h1 h1, 0 into h2 is 0. So this is minus h1 by modulus of a vector in the two-dimensional plane is square root of h1 square plus h2 square. Modulus of a vector. Now I have to see whether this limit exists. If the limit exists, then it is differentiable. If the limit doesn't exist, it is not differentiable. So, it is equal to multiply h1, limit h1 into 0 h1 cubed minus, take the LCM, h1 cubed minus h1 into h2 square by root of h1 square plus h2 square. Don't forget the modulus, because the modulus stands for the length of the vector in R. So this is limit h3 into 0. So this is limit h3 into 0. This is h1 h2 square by, so I am taking the LCM here, so h1 square plus h2 square will come down. So this is going to be h1 square plus h2 square by h1 square plus h2 square whole power 3 by 2. Whole power 3 by 2. And this limit must exist. Limit in two dimension, remember, it will exist only when the limit exists in whatever direction the point approaches the origin. So I am going to take h1 equal to h2, put h1 equal to h2. That means I am taking the limit along the line y equal to x. Along the line y equal to x. This is h1 equal to h2. So along the line y equal to h, I am taking the limit. So h1 equal to h2. When you put h1 equal to h2, you will get limit h1 tending to 0. When h tends to 0, h1 will tend to 0. And this will become h1 cube by, this will become 2 h1 square, that is 2 power 3 by 2 into h1 square whole power 3 by 2 will be h1 cube. So h1 cube gets cancelled, so the answer is 1 by 2 power 3 by 2. And so you see that the limit is not equal to 0. Limit is not equal to 0. That means the definition is violated. Because the definition that limit h tending to 0, that limit must be equal to 0. Here it is not equal to 0. It's a non-zero number. Therefore, that A does not satisfy the condition in the definition. Therefore, the function is not differentiable at the origin. So you see that I have just given you the definition of differentiability of a function of several variables at a point x. Based on the definition, I have quoted a theorem. That theorem is very important. The Jacobian will exist. And based on that theorem, I have done a problem. And this is how you have to build up and develop the subject. So with this, I would like to close my inaugural address. Once again, I thank the organizers, the conveners of this program, the management of St. Joseph's College for giving me opportunity to deliver the inaugural address. Thank you one and all. For any questions, you are most welcome. I'll give you my number. You can contact me on the phone. Thank you.
We wish to express a gratitude to our Chief Guest Professor R. Lawrence Joseph Manoharan, Retired Head, Department of Mathematics, St. Joseph College, Trichy, for being with us on this event. Your presence and gentle words are a source of encouragement for all of us. Thank you so much, sir. It takes 1 hour of preparation for each minute of presentation time. The right word may be effective, but no word was ever as effective as a rightly timed pause. Now, I welcome Dr. Gino Cadwin, Assistant Professor, to ignite the dynamics of the workshop MATANA 2020.
Hello everyone. It's my immense pleasure to invite you all to participate in the workshop on mathematical analysis. The objective of this workshop is to provide all of you a learning experience on mathematical analysis. I hope that all of you will enjoy the learning experience during the workshop from the resource persons of various reputed institutions. I want to outline the dynamics of the workshop. Every day the session begins at 9:30 am and a series of lectures will be published one by one. The published videos will not be removed from the YouTube during the workshop. So you can watch the lectures at any time you want on the day. At the end of the lectures on each day, quiz and assignments will be there based on the lectures. Though the lectures are not live, you can get clarifications and discussions and interactions with the resource persons via Google Classroom. You are encouraged to solve problems and discuss the solutions within Google Classroom. You are also requested to submit the feedback form daily through the links given. I wish you all a successful learning experience. All the best. Thank you.
Thanks Dr. Gino for your deep briefing on workshop of mathematical analysis. Finally, technology will never replace great teachers, but technology in the hands of great teachers is transformational. A truly amazing maths teacher is hard to find and impossible to forget. Thank you very much for your kind and active engagement in this inauguration. Thank you.